Today I'll talk about Lagrange interpolation. So here is the problem statement. Given experimental data of reaction rate constant K at different temperature T, estimate K at T is equal to 350. So that we have to. Today I am going to talk about Lagrange interpolation. So here is the problem statement. Given experimental data of reaction rate constant K at different temperature T, estimate K at T is equal to 350 Kelvin using Lagrange interpolation. So here is the T versus reaction rate constant data. From that we have to calculate K at T is equal to 350 Kelvin. Now here first we have to learn what is Lagrange interpolation formula. So the Lagrange interpolation formula is P of T, means polynomial of T, so that is equal to summation of I to 0 to n Ki into Li of T. So this is Lagrange coefficient, and then that can be calculated by using this formula: j to 0, j naught is equal to I to n T minus Tj, Ti minus Tj. So I'll show you, how we will calculate the Lagrange coefficient. So now here, so Lagrange coefficient, so here that how many data are here? So 1 2 3 4 5. So 5 Lagrange coefficient we have to calculate. So that is starting from 0 to 4. So L0T, so here that T is that temperature, and then T1, T minus T1, T minus T2. So here we had starting from T0. So T0 will not be in that numerator. So T minus T1, T minus T2, T minus T3, T minus T4. Then it will start from T0 minus T1, T0 minus T2, T0 minus T3, T0 minus T4. So in that top it will start from T minus T1, but T0 will not be there, and bottom it will start from T0 minus T1 with other multiplication with subtraction. So now L1T, similarly T minus T0. So here that T1 will not be in the top, that numerator. T minus T0, T minus T2, T minus T3, T minus T4. Now here, that is here T1 minus T0, T1 minus T2, T1 minus T3, T1 minus T4. Remember here T1 minus T1 will not be there, otherwise it will be 0. So again for this L2, so again that is T2. So T2 will not be in the top, means numerator. So T minus T0, T minus T1, T minus T3, T minus T4, like that way you will get L0, L1, L2, L3 and L4. Now here we have to substitute all the data, and then we have to calculate that different coefficient. Now here I am going to calculate that. So now here if you see here, so T is nothing but 350, okay, and T1, T2, all these data are given. So now here 350 minus 320, 350 minus 340, 350 minus 360, 350 minus 380. Now here, so T0 value, this is T0 value, T0 minus T1, then T0 minus T2, T0 minus T3, T0 minus T4, okay, and this is T minus T1, T minus T2, T minus T3, T minus T4. So if I plug and do the calculation, we will get the coefficient is 0.2344. Similarly L1 will be minus 0.1562. Similarly L2 350 will be 0.4688. Similarly L3 of 350 will get 0.5469, and L4 of 350 will get minus 0.0938. So after getting all this coefficient, so we plug into the formula and we will get the reaction rate constant. Now we have all these, that Lagrangian coefficient, so L0, L1, L2, L3, L4. Now here we have to put that L0 of 350, and then this is at 300, that K value. Similarly L1 of 350, and then K at temperature whatever 350, then something 320, 005. So we have to plug that 005. Similarly that L2 and K at next temperature, then L3, and then L4, and then we have to put corresponding that K value. Now after that, after adding all these value, if we multiply, we'll get this value. If we multiply it with L1 with K value, so that minus 0.781. So after getting all this value, we have to put and then add, then we'll get K 350, so that will be 0.01176 mole per second. So estimated rate constant at K is 350 at K at 350. So at temperature 350, K will be 0.01176. You can check that. So here that 350 means it will be between 340 to 360. So range should be 0.009 to 0.0015. So we got the result is 0.01176. 0.0116 lies between 340 and 360. So our result is okay. So now that way we can calculate the reaction rate constant at particular temperature. So that's it about Lagrangian interpolation. Thank you.